800 years ago, a civilization with no factories, no foundries, no fixed cities, and no supply chain conquered more territory than Rome did in 5 centuries. They didn't win because they were brutal. They won because every piece of equipment they carried was a precision-engineered solution to a specific physical problem. And some of those solutions have never been improved upon. Modern armies spend billions on logistics. Modern engineers spend their careers on materials science. Modern architects spend decades on climate-resilient structures. The Mongols solved all 3 with leather, bone, horsehair and silk, while moving 100 miles a day across the most hostile terrain on Earth. We've been taught to measure intelligence by the tools available, not by the problems solved. 15 distinct innovations detail this operational paradigm. Each represents a localized engineering framework designed to maximize resource efficiency across varying geographic profiles. This analysis tracks how a nomadic baseline achieved optimized logistics, looking at why organic composite matrices rival modern material alternatives, down to the primary mechanical innovation that made the empire's mobility possible. Operating with an active deployment of 100,000 riders across 6,000 miles of varying terrain required an absolute elimination of material waste. Every sedentary empire treated rivers as natural defensive barriers. Build your fortress on the far bank, destroy the bridge, and wait. The enemy stops, the campaign stalls, the season turns. The Mongols made rivers irrelevant in under an hour. The tool was called a Tulum. At its core, a dead sheep. But what the Mongols did with that sheep was a masterclass in material chemistry. The hide was removed whole, every limb opening, every seam intact, then tanned and cured in a solution of oil, water and salt. Historical Chinese texts called the result cooked leather, permanently elastic, completely non-porous. A courier would inflate it with his lungs, seal the openings with oil-dipped twine and lash it beneath a lightweight willow frame. A single bag floated a man and his gear across a river in minutes. But the engineering scaled. Small tactical configurations utilized 13 unified bags to float offensive units. For heavy transport, Imperial logistical teams linked hundreds of these non-porous bladders beneath modular timber decking, creating stable, buoyant platforms capable of transporting structural, artillery and supplies across major river systems without halting the army's advance. This system transformed unpredictable waterways into high-velocity supply corridors, moving significant tonnage without the need to construct fixed masonry bridges. The Mongols didn't just build a better bow, they engineered a better human trigger mechanism. Every archer in the ancient world faced the same constraint. The Mediterranean draw, 3 fingers, palm up, places the load across the index, middle and ring fingers. At draw weights above 60 pounds, the tendons fatigue. Above 80, the string torques on release. Above 100, you risk permanent nerve damage. The Mongols solved this with a ring carved from jade, bone, horn or antler, worn on the thumb. The first thumb joint acts as the fulcrum. The bowstring sits against the ring as the load. The index and middle fingers reinforcing the thumb act as the effort handles. A second-class lever, the strongest mechanical configuration available to the human hand. The palm-down Mongolian draw is biomechanically stronger than any finger draw. The polished ring surface creates a friction-free release point. The string slips off clean, zero torque, zero twist, maximum velocity. Modern compound bow shooters use a mechanical release aid for exactly the same reason. The Mongols built the same principle from carved bone 800 years earlier. The trigger was solved. The fuel problem was next. The Mongol army carried no supply wagons, no grain carts, no salted pork barrels rolling behind the cavalry on ox-drawn wheels. Their food supply was the physics of the Gobi Desert itself. The ration was called Borts. Lean meat, beef, camel, horse, goat, sliced along the grain into strips, then hung under the rafters of a ger as winter arrived. What followed was a two-phase thermodynamic process modern food scientists classify as atmospheric freeze-drying. During the onset of sub-zero winter temperatures, the cellular moisture within the tissue crystallized rapidly. Continuous low-humidity winds moving across the steppe drove a process of atmospheric dehydration. At sustained freezing thresholds, the ice crystals within the fibre matrix sublimated, evaporating directly into gas without returning to a liquid phase, completely bypassing the moisture window required for microbial or bacterial proliferation. As temperatures shifted, the remaining structural fluid was drawn outward through continuous capillary migration. This process yielded a non-perishable, highly dense protein isolate, reducing raw tissue weight by approximately 80%, while preserving long-term caloric integrity inside a compact leather casing. A walnut-sized portion dropped into boiling water, rehydrated to 2.5 times its dry volume in minutes. NASA freeze-dried space rations used the same sublimation physics. The Gobi Desert was their vacuum chamber, 8 centuries before the space program. The food problem was solved by weather and geometry. The shelter problem required something more elegant. Universally classified as a rigid, semi-permanent tensegrity structure, the Zhir utilizes a circular, interconnected skeleton engineered to withstand 70 mph winds and temperature swings of 200 degrees Fahrenheit. The entire system can be assembled by 2 people in under an hour, packed onto 2 camels and reassembled identically on the other side of a mountain range. Its foundational framework relies on a collapsible lattice wall called the khana, constructed from preformed willow slats. At every intersection, these elements are secured using flexible camel rawhide pins, rather than static, unyielding joints. Where rigid configurations concentrate localized stress and fracture under heavy loads, the rawhide tied lattice flexes and rotates at each individual pinpoint. This dynamic movement allows the frame to absorb and distribute kinetic energy across the entire circular circumference simultaneously, ensuring no single structural element ever reaches its mechanical failure threshold. The circular profile handles the rest. Wind striking a flat wall creates direct pressure. Wind striking a dome is redirected around the curve. The Zhir gives the wind nowhere to push. The insulation, thick sheep wool felt, uses hollow core fibres to trap static air. The same principle as modern double-pane glass. The air doesn't move. The heat doesn't leave. Here is the part worth sitting with. This structure was not designed by an architect with a drafting table. It was refined over centuries by people whose lives depended on getting the physics right, and they got it right. The shelter moved with the army. The horse had to move with it, and that required solving a problem modern equestrians still get wrong. Functioning primarily as a mechanical weapon stabilization platform rather than a simple mounting asset, the High-Flange iron stirrup provided a rigid, wide structural base for the rider's foot. While primitive leather loops merely helped a rider remain seated, they failed to support a standing posture. A mounted archer who cannot stand cannot achieve stability. The horse's violent vertical impacts travel directly through the saddle and into the rider's upper torso, breaking their aim. The Mongol design utilized deep, flat-bottomed iron castings. Standing clear of the saddle seat during a high-velocity gallop allowed the rider's knees and hips to act as an active suspension system, isolating the upper body from the kinetic vibration of the horse's stride. The shoulders, arms, and bow hand remained stationary in 3-dimensional space, while the horse moved beneath them. Mongol archers released during the brief moment when all 4 hooves were simultaneously off the ground. 0 platform vibration. Maximum accuracy. Film crews use a Steadicam for exactly this reason, a mechanical gimbal that isolates the camera from the operator's body movement. The Mongol stirrup was a human Steadicam, built from iron, 800 years before the concept had a name. The platform was stable, but the horse carrying it had to survive the campaign. Every medieval European saddle concentrated the rider's weight directly onto the horse's spinal column. This is not a design flaw that went unnoticed. It is one that went unsolved for centuries. Localized spinal pressure caused friction sores, muscle damage, and fatigue. A horse under a European knight was operationally degraded within 40 miles. By 200, it was done. The Mongol Suur saddle solved this with geometry. Carved from birch or larch, the Suur featured broad, flat side bars running parallel to the horse's spine. When the rider sat, his weight transferred entirely onto the horse's ribcage. The spine carried nothing. No pressure points, no friction sores, no spinal fatigue. The result was a horse that travelled double its normal daily distance without breaking down. The high cantle and raised pommel acted as physical locks, keeping the rider seated through high-speed combat manoeuvres without gripping effort. Modern equestrian saddle-fitting science confirms this principle exactly. The Mongols had it solved in the 13th century. The logistics network ran on healthy horses. Healthy horses ran on correct geometry. The Mongols needed a portable, indefinite source of calcium, protein and fat. No refrigeration, no cooking, no resupply. They built it from milk. Animal milk, cow, yak, goat, camel, sheep, was boiled until dense curds formed, strained through cotton and pressed under heavy stones until every trace of whey was expelled. The compacted mass was shaped and placed on wooden boards atop the gyre to dry under the summer sun and steppe wind. Drying continued until the curd became as hard as stone. That hardness is the engineering. As moisture leaves, the water activity level, the measure of free water available for microbial growth, drops below the threshold required for bacteria, mold, or lipid oxidation to survive. Below that threshold, nothing spoils. The product is chemically stable indefinitely, kept in breathable linen bags for years, hard enough to resist a cutting tool, dissolved in warm water for a nutrient-dense drink. The same water activity science governs modern military MRE shelf life engineering. The Mongols achieved it with a stone and a rooftop. Moving information across a continent at speed required a different kind of infrastructure entirely. The Mongol Empire at its peak covered over 9 million square miles of contiguous territory, administered effectively through structured transit corridors. That was only possible because the Mongols built a physical authorization system that modern network engineers would recognize immediately. The Paiza was a tablet, gold, silver, bronze or iron, inscribed in Fagspar, Uyghur or Persian script, invoking the absolute authority of the Great Khan. Rank was encoded in material and imagery. Gold tablets with a tiger's head went to senior military commanders. Tablets engraved with a gyrfalcon went to high-speed state couriers. Presenting a Paiza at any station legally obligated local administrators to provide fresh horses, food, lodging and armed escorts immediately without negotiation. Defiance was punishable by execution. This is an SSL security token, a physical cryptographic key that authorizes a data packet, a human courier, to bypass local administrative firewalls and access system resources at full priority. Tiered network access control, stamped into metal 600 years before the concept of a computer network existed. The key unlocked the network. But first, the gear holding all of it together had to survive a Siberian winter. Most medieval armies went operationally non-functional in deep winter. Leather boots froze and cracked. Armour laces snapped. Bowstrings absorbed moisture and lost tension. The campaign stopped until spring. The Mongols preferred winter campaigns. Their equipment worked when everyone else's didn't. The compound was simple. animal tallow boiled with birch bark tar into a thick, viscous grease. When massaged into leather, the two components performed separate functions simultaneously. The tallow penetrated deep into the collagen fibre structure, preserving natural elasticity. The tar sealed the surface pores against moisture. Water could not enter. Ice could not form inside the material. Boots and armour laces remained flexible and crack-resistant at temperatures that turned untreated leather into brittle glass. Modern leather preservationists use lanolin and wax compounds on the same principle. Lipid penetration combined with surface sealing. The Mongols built the same chemistry from rendered fat and tree bark. The gear held. The question was how to keep 100,000 horses moving without burning them out. The Mongol cavalry didn't move fast because they had better horses. The steppe horse was compact, short-legged, and unremarkable by the standards of Arabian or European war horses. What it was part of a system. Every warrior travelled with a loose string of 4 to 5 horses, not led on ropes, but running free alongside the rider, trained from birth to follow like dogs. At the first sign of lactic acid buildup, a slight change in gait, elevated breathing, the rider transferred his saddle to a fresh mount mid-gallop and let the tired horse recover with the herd. No horse ever reached critical fatigue. The sustained pace, 100 miles per day, indefinitely. Modern data centres use the same logic. Dynamic load balancing distributes demand across multiple servers so no single unit reaches critical load. The Mongols ran the same architecture on 4 legs across the Eurasian steppe. When the grass ran out, these horses foraged beneath deep snow. The army carried its own fuel supply, and that fuel supply fed itself. The horses kept moving. The men riding them faced a different threat, one that could blind an entire cavalry force in a single morning. Photokeratitis, snow blindness. Ultraviolet radiation reflected off a flat snowfield burns the cornea in hours. An army that cannot see, cannot fight, cannot navigate, cannot survive. The Mongols solved this with woven horsehair and the physics of the pinhole. Dense, dark horsehair was braided into horizontal bands with narrow viewing slits. The dark fibres absorbed scattered UV glare before it reached the eye. The narrow slits restricted incoming light to a single focused horizontal plane, the pinhole optic principle. The cornea was shielded from UV burn, and visual acuity improved. The restricted light path sharpened long-distance definition the same way a camera's depth of field sharpens when the aperture narrows. No fogging, no scratching. No lens failure at -40 degrees Fahrenheit. Modern polycarbonate lenses crack in extreme cold. Horsehair does not. The same pinhole principle appears in precision optical instruments, slit lamp ophthalmology equipment, and the aperture mechanics of every camera ever built. The Mongols wove it from a horse's tail. The eyes were protected. The command structure needed to keep moving, and that required infrastructure on a scale that still impresses modern civil engineers. Every sedentary empire shares the same structural vulnerability. The capital is a fixed point. Fix the capital, fix the target. Besiege the capital, besiege the empire. The Mongols eliminated the fixed target. Full-scale dewars were constructed permanently atop massive wide-axle wooden wagons called tereg. The largest axles measured up to 20 feet across, distributing load across uneven terrain to prevent tipping. Teams of up to 22 oxen pulled them in coordinated columns. These were not carts with a tent on top. These were complete operational structures, administrative offices, living quarters, command centres, rolling across continents at campaign pace. The Khan held court, issued orders, and received intelligence from the same room he had occupied the week before, 300 miles away. The United States Air Force operates the E-4B Night Watch, airborne command post designed to keep National Command Authority functional after a first strike destroys fixed ground infrastructure. Continuity of command, regardless of geography. The Mongols built the same concept from wood and oxen in the 13th century. The command moved, the warriors were protected, but the most elegant protection on this list wasn't armour. It was textile. A common historical misconception claims Mongol warriors wore silk undergarments because the fabric could stop an arrow. Ballistic testing disproves this. A high-velocity arrow easily penetrates a single layer of raw silk. The true innovation lies entirely in post-impact wound mitigation. When an arrowhead pierced the outer lamellar armour and entered the flesh, it failed to cut cleanly through the high-tensile silk fibres. Instead, the twisting tip tightly wrapped the fabric around itself, forming a protective sleeve between the metal head and surrounding muscle tissue. This localized containment prevented barbed edges from severing critical blood vessels as the warrior moved. Rather than digging into the wound channel, a field medic simply grasped the edges of the silk shirt and pulled gently outward. The arrowhead, insulated by its own fabric sleeve, slid smoothly out along its entry path without causing secondary tissue tearing or leaving infected debris behind. Because medieval combat mortality was driven primarily by subsequent hemorrhage and infection, this textile framework provided an advanced trauma intervention strategy centuries ahead of its time. Administering over 9 million square miles of contiguous territory in near real time required a communications infrastructure unmatched until the electric telegraph. The Ortoo network was a precision data transfer system built from specialized relay nodes spaced exactly 25 to 30 miles apart along imperial transit corridors. Each fortified outpost maintained up to 400 fresh horses and relief couriers on permanent standby. Priority couriers wore specialized belts of bells, alerting the upcoming station to have a fresh mount saddled and waiting. Swapping horses mid-route took seconds, allowing couriers to sustain a full gallop across 250 miles in a single day. While the Roman postal system averaged 50 miles per day, and the 19th century Pony Express required twice as many stations to cover a fraction of the distance, the Ortoo operated with strict mechanical efficiency. It functioned identically to modern packet switching networks. Data packets, the couriers, were forwarded from router to router, refreshed at each node to prevent physical degradation, and prioritized by a physical encryption key, the Paiza token. Modern industrial engineers utilize carbon fiber, aerospace polymers, and finite element analysis to optimize ballistics. Yet these materials struggle to exceed the mechanical efficiency of an organic laminate matrix assembled on the steppe 8 centuries ago. The Mongol composite recurve bow utilized 3 distinct material layers engineered for opposing physical forces. The inner belly consisted of compressed horn, a material that stores energy under compression, like a heavy steel spring. The outer back layer was wrapped in animal sinew, a highly elastic material that resists tension and releases it explosively. These opposing layers were bonded around a structural wooden core using isinglass, a high-strength waterproof adhesive rendered from sturgeon bladders that resisted draw weights exceeding 160 pounds. Without delaminating. Because the bow was built with a pronounced forward reflex geometry when unstrung, the laminate maintained extreme mechanical tension throughout the entirety of the draw cycle. Rigid bone extensions at the tips, the ears, acted as structural levers, minimizing dead mass and transferring roughly 80% of the stored energy directly into heavy, armor-piercing projectiles. While monolithic wooden longbows required immense vertical scale to prevent grain shear under load, this compact architecture compressed elite kinetic output into a specialized frame optimized for high-speed, mounted warfare. Look across all 15 of these innovations, and a single pattern emerges. Not one was built for elegance. Everyone was built to solve a specific physical problem. River crossings, wound extraction, information transfer, load distribution, thermal management, with minimum material and zero margin for failure. The Mongols didn't over-engineer, they solved, and the solutions were so precisely matched to the underlying physics that 800 years of industrial progress hasn't fully replaced them. The cutting edge, it turns out, has always been pointing backward. Most of what this channel covers works exactly like that, not forgotten because it failed, but set aside because something else was more profitable. If recovering that kind of knowledge matters to you, the next story is one click away.